All right, welcome to Physics Video 4.4. We're going to learn about projectiles today. I will comment that if I'd had a little bit more time, I would have liked to have inserted in a couple other videos to sort of help you better understand this concept. So we'll talk about this more in class. The big thing here should be kind of getting down what I tell you here. Some of it's going to seem weird and maybe tough to visualize. I'll give you some more examples in class when I see you next that'll hopefully help you visualize it a little bit better, since I didn't have time to edit in the videos I wanted to. So anyway, objectives. By the end of this video, you should understand what a projectile is and be able to give examples. And you should understand and be able to apply the two big rules of projectiles. All right, so here we go. So far in this chapter, we've seen how a force can change the speed of an object, right? Well, actually, that's something we've seen, since the beginning of forces, that when you put a force on something, you can make it go faster or slower. And more recently, in circular motion, we saw how a force could change the direction of an object, right? Because the centripetal force pulls the object inward, causes it to turn and go in a circle. All right, projectiles are cool because it's an example of a situation where the force changes both the speed and the direction of the object, which we really haven't looked at too much yet. All right, so here we go, projectile. Technically, a projectile is any object in free fall. All right. However, usually when you talk about a projectile, you're talking about an object that has horizontal motion as well. All right. So again, technically speaking, if you drop a ball or throw a ball straight up into the air, throw a ball straight down, it's a projectile. Usually, though, when you think of a projectile, you would imagine throwing the ball at some angle or something. So I'm going to do this real quick. So if you drop a ball and it goes straight down, that's a projectile. If you take a ball and throw it straight up, so it goes up and comes straight back down, projectile. All right, and we've done problems like that. What we haven't done yet, and this is where it becomes more interesting, is if you take that ball and instead of dropping it, you toss it sideways, so it follows a curved path. That is usually what you're talking about when you talk about a projectile. Or if you imagine kicking a soccer ball, right? The soccer ball is going to go and apparently explode when it hits the ground. So that's what a projectile is. All right. So the focus of this chapter is going to be this kind of stuff, where the projectile is moving, either down or up and down, but also moving horizontally while it does it. Okay. In the last video, we talked about horizontal velocity and vertical velocity. That idea is going to be super, super important in this video. Okay. Because at any given instant, like if you imagine this soccer ball here, it's going this way, right? So at that moment, it's going to have some horizontal velocity and some vertical velocity. All right. And the two rules that I'm going to tell you here in a minute basically tell you what the horizontal velocity does and what the vertical velocity does. Okay. And to be honest, if you have a good understanding of Newton's laws, you already know the answer to this. So anyway, so that's what a projectile is. And then, as I was saying before, a projectile changes both speed and direction, right? And that's what this says down here. When you throw a ball, the only force on it is the force of gravity, and it causes the object to do two things. It changes direction, right? Like if you throw a ball this way, it doesn't keep going that way forever, right? It goes like this. It changes direction because gravity is pulling it downwards. Okay, so that's why it follows a curved path. And in addition to that, it changes speed, right? Because as it's going up, it's working against gravity, so it slows down, slows down, slows down, slows down, and then on the way down, it speeds up, speeds up, speeds up, speeds up. Okay, so it's both changing direction and changing speed. Okay, so kaboom. We've already seen this. Kabam. All right, the two big rules of projectiles. All right, the remainder of this video, I'm going to focus on this right here, the two big rules of projectiles. If you understand these two rules, you can solve any projectile problem in the universe. So there you go. Here we go. Here's the first big rule. First big rule tells us that the horizontal velocity of any projectile will always remain constant. The horizontal velocity of any projectile will always remain constant. All right. That's just an extension of Newton's first law. You guys already know this. All right. Think about it. After you throw that projectile, the only force on it is gravity, right? What that means then is that there's no horizontal forces on it, right? Because gravity just pulls stuff downwards, right? So there's nothing pushing it either this way or this way, right? There's no forces pushing it horizontally. And because of that, our net force in a horizontal direction is 0. All this is saying is there's no forces acting on it horizontally. Remember, x is horizontal, right? In math class, you've got your x and y axes. Okay, so there's no forces on it horizontally. And since there's no forces on it, it's not going to accelerate horizontally, which means the horizontal velocity is going to stay constant. Your Vx is always going to be the same. Okay, so after you throw your projectile, however fast it's moving horizontally, it's going to keep moving at that rate horizontally. And this last part, which these little guys are covering up, is super important. So the end result, what that means, is this. Every second that a projectile is in the air, it's going to move the same distance horizontally. Every second that the projectile is in the air, it's going to move the same distance horizontally. All right, so let me give you an example of that. All right, it says, suppose a car drives horizontally off of a cliff at 20 meters a second. All right, so, okay, so there's our car, which I've drawn here. Its velocity as it drives across this cliff top is all horizontal. So I wrote the velocity is the same as the horizontal velocity, right? Because it's moving horizontally at 20 meters a second. Okay, notice it's not moving vertically at all, right? So our Vy is 0. There's no motion up or down. Okay, so what does it mean to go 20 meters a second? That means every second you go 20 meters. All right, so here's what's going to happen. The car is going to drive off the cliff. This is not drawn to scale, so the car is going to go, right, and hit the ground like that. Okay, so what I'm going to do for a minute is completely ignore the vertical motion and just focus on the horizontal motion. Okay, what this is telling us, what the first law tells us, is that this horizontal velocity is going to stay constant. All right, so if the sun was directly overhead and we watched the shadow of the car down here moving across the ground, that shadow is going to go 20 meters every second. Okay, so let's do this. Let's imagine that from the edge of the cliff to here is 20 meters. So there's 20 meters. And then from here to here is another 20 meters. I'm trying to space these apart evenly. From here to here is another 20 meters. From here to here is another 20 meters. Are those about the same distance apart? No, but whatever, you get the idea. To here is another 20 meters, and to here is another 20 meters. Okay? So what that means is, in the first second that the car is in the air, it's going to go 20 meters. So it's going to go from here, from the edge of the cliff, to right there, right? 1 second later, it'll have gone another 20 meters. So it'll be right there. 1 second later, it'll have gone another 20 meters. So it'll be right there. 1 second later, it'll have gone another 20 meters. 1 second later, another 20 meters. And in the last second, it goes the last 20 meters and hits the ground. Okay, so these lines, because I drew this by hand, it doesn't really look like it, but 20 meters, 20 meters, 20 meters, 20 meters, 20 meters, 20 meters. All right, the car goes horizontally 20 meters every second. So every second, the car goes horizontally 20 meters. Okay? Dang it. I am determined to underline that. There we go. All right? That's what the first rule tells us. Okay? Now, at the risk of getting ahead of myself, the next thing we're going to do is the second law, or the second rule. All right? The second rule tells us about what happens vertically. All right? So here's what happens vertically. While the car is in the air, gravity is pulling it down. Okay? So the car at the beginning wasn't moving vertically, right? But then as gravity pulls it down, it's going to go down faster and faster and faster. And so what happens is the distance that it travels vertically gets bigger and bigger. So look, in the first second, it went from here to there vertically, right? So it only fell a little distance. In the next second, it fell down to there. In the next second, it fell to there. In the next second, there, right? In the next second, there. And in the last second, there. So vertically, look what's happening. The distance it goes each second gets bigger and bigger, right? In the first second, it only falls a little distance. Turns out to be 5 meters. Again, this is not drawn to scale. In the next second, it's going to go farther. In the next second, it goes farther, 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 until it hits the ground, right? Okay? So that's where we're headed, which is our second rule that tells us about the vertical motion. Kabam! There it is, big rule number 2. Says any projectile will fall with a vertical acceleration of negative 10 meters a second squared. Notice this is just the acceleration of gravity. Okay, regardless, irregardless if you prefer, of any horizontal motion it may have. In other words, no matter what the projectile is doing horizontally, if it's not moving horizontally or it's moving horizontally at 1 billion miles an hour, well, not 1 billion, but if it's moving horizontally, it's still going to fall down at the same rate. Okay, so what that means to us is this. Oh, sorry. How do we get that? Why do we know that? Well, that's basically just an extension of Newton's second law, right? Look, the force of gravity is the only force on it. So our net force vertically is just the force of gravity. Okay, and if you take the force of gravity and divide it by mass, it gives you the acceleration of gravity, right? That's Newton's second law, basically. So our acceleration vertically is just negative 10 meters a second squared, right? It's going to accelerate downwards at the acceleration of gravity because the only force on it is the force of gravity, which means that every second the vertical velocity will decrease by 10 meters per second. Okay, remember, decrease means it's getting more negative. Okay, so I have 4 minutes here to do this last example. All right, so here's our last example. Suppose you had 5 cars driving horizontally off a cliff that was 5 meters tall. Okay, so there's our car that's going to drive off, or cars that's going to drive off a cliff. You can only see the one in front, the other ones are behind it. All right, so they are all driving horizontally at some speed, and they're going to go off the cliff. Okay, now I gave you the height here for a reason. The cliff is 5 meters tall, right? And remember, what the second law tells us is how fast the car is going horizontally doesn't matter. Okay, that any projectile will fall down at the same rate. So the fact that this height, which we're going to call vertical displacement, is 5 meters, negative because it's going to go down 5 meters, allows us to find the time. All right. So last chapter, or first chapter rather, we learned this equation. We learned that equation, which worked if, if your VI is 0. I'm going to modify that equation right now to give us some vertical information. Okay, so here I modified it to tell us that it's vertical that we're talking about. Okay, basically I just change an X to change an Y to indicate that it's vertical. And basically, long story short, what I figured out here is that it's going to take 1 second to fall 5 meters. Hopefully you guys remember that. That was something that we figured out, that in the first second that an object is in free fall, it'll fall 5 meters. Okay, so the idea is all 5 of these cars here, because they're falling from a cliff that's 5 meters tall, they're all going to take 1 second to fall. Okay, which seems counterintuitive. It feels like this car, this last car that's going super fast, should sort of be in the air longer, right? Because it's going faster, all right, is what people tend to think, all right? But that's not the case. All right, so let me clear up the board here. Okay, so let me show you what's going on. So the first car is going really slowly off the cliff, but it's going to take 1 second to fall. So what happens is in that 1 second, it's going to go, all right, and it lands. Because it was going 2 meters per second, it's going to land 2 meters away, right? Because it took 1 second to fall, and in 1 second, it's going to go horizontally 2 meters. So it's like 1 Mississippi, right? Okay, the next car is going faster. It's going 10 meters a second. So in the time that it takes it to fall, 1 second, it's going to just go farther. It's going to go 10 meters in that 1 second. So car B is going to go 1 Mississippi, right? So that it lands 10 meters away. All right, I'm going to run out of room here because my board is not wide enough. The next car is going to go 50 meters in that 1 second, right? So it's going to go 1 Mississippi. And the next car is going to go 100 meters. So it's going to go, right, 1 Mississippi. And it's going to land way over there off the screen, right? So the idea is no matter how fast the car is traveling, they're all going to hit the ground at the same time. They're going to go, mer, 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 mer. Okay, they all hit the ground in the same time. The only difference is how far it moves horizontally in the time that it takes to fall. Okay, I'm going to stop there because we're right under 15 minutes. I'll give you guys some more demonstrations in class, to help explain this. All right, so here we go.